Okay. Hello, welcome friends. Welcome to the part 2 of chapter 3 of my deep learning course. As I told you uh, in all previous lectures, the slides are for Professor Ali Barihi for the applied deep learning course at University of Toronto. Okay, let's continue with the overfitting and underfitting. Okay, just for a quick review, we have seen that overfitting happens in three situations. First is that the model has a large capacity. Second is that our training data set is very small. Small is something not absolute. It is something what's this? Oh, okay. It's something relative, not absolute, but we are talking about the training dataset size with respect to the module size. Okay, so the first and second one are somehow related to each other, and the third situation is that when the training iterations are large, we sometimes the co-adaptation happens, and so what can we do for reducing this overfitting or removing it? The first one is that to tune the hyperparameter to restrict the neural network's capacity. For example, in the validation set, we can consider different number of hidden layers, which is the hyperparameter. The hidden layer number is the hyperparameter, and yes, it's the first approach. The second approach is that we can increase the data set by data augmentation. For example, we can rotate or shift or blur or some other transformation on the image, or maybe if it is NLP, other data augmentations for text. We can perform this, and by doing this we can mitigate this second one, which is the smallness of the training dataset. We can increase the dataset by data augmentation. And the third one is the data regularization of the empirical risk. It's different from for example, regularizing the data. So it helps us to penalize the solution, and we consider a penalty term for the regularization term. And so there are different types of regularization, for example dropout, or for example L1 or L2 regularization, which we will discuss in the rest. Okay, first of all I want to talk about regularization. Okay, as you may consider, or as you may remember, we had an example of overfitting a polynomial term with neural networks. For example, when we set p to 5, and yes, as you can see, for example, after in time 2 we reach a good point, but as we continue in step n, we reach a bad point. So here you can see the empirical risk. The empirical risk reduces, but it's not good in this part, in spite of the fact that it has been reduced, but it's not good yet. Okay, so we should modify the empirical risk now, and we want to stop the empirical risk from dropping after T2, which is the best iteration that we have. Okay, for example, consider the current situation that the empirical risk in time 3 is 0.001, and in time 2 0.01, and in time 0 at the start 100. Okay, so uh, as you saw before, the W which we are training it becomes larger. We can mm, uh, so uh, when our risk becomes too small, if we uh, if we consider the W which is large, it tries to keep the empirical risk large. Okay, it's you will see in the next example. If we consider this plus the norm 2 of W0, it would be 100. Okay, because W0 is 0, and there our head of W0 is 100, as you can see, but the W power 2 would increase as time goes on. As we can see here, the best iteration is T2 that we wanted. Okay, okay, we don't want to get from W2 to Wn, and with doing this we have penalized the risk using a regularization method. For example, the method that we have used is L2 normalization, because we had calculated the W to the power of 2, so it is L2. Okay, and the formal definition of this regularization is as follows. We minimize the penalized form of the empirical risk. As you can see, the pi of W can be anything. It should not be necessarily the thing that I showed you, which was L2 normalization. Okay, there are some classical approaches for this regularization term. We would not consider any possible pi of W because we want to reach our solution as soon as possible, so we will see the best practices of this regularization term that have been performed in the context of regularization in deep learning. Okay, as you can see, L2 or Tikhonov regularization, we added term proportional to W2. By proportional, I mean we add a multiplier lambda, which can be, for example, 1/2 or anything that you can consider, but it's not really important. The important thing is that we have this term. Okay, so when we have very large rates, it seems that we are not correct. Why? Because we want our solution to be as sparse as possible, to have the least possible dimensions, so it has reduced all the irrelevant dimensions. So the optimal solution probably is small, so we don't want large answers. Okay, the second one is L1 or less for regularization. Is the here we had it to power of 2. Here we have the abs of it. It means we so we use absolute value of W here, and as you can see, again we have a term of lambda and the sigma over the absolute value of all of the W's. By all of the W's, I mean all of the dimensions of this W. Okay, as you can see, this will again force W to be sparse, to have many zeros. It's somehow different from the previous one. The previous one does not necessarily concentrate on the sparsity, but it's usually becomes a sparse, but the main concentration for a sparsity happens in L1 or less regularization, as you can see here. Okay, and we can go to the next one, which is dropout, and very popular method invented by, I think, Jeffrey Hinton. Let me say, yes, Jeffrey Hinton. He won the Nobel Prize some weeks ago. Yes, and okay, dropout is another way that was proposed in 1214 officially, and it means that during training we deactivate and delete some nodes of the neural network randomly. Noting it should be random, so if it is not random, it is not working as well as this approach. Okay, as you can see in this network, it is dense. All of the edge nodes are activated, but as you can see here, some of the nodes are deactivated here. Compare it. As you can see, this node is deactivated, it has no outputs. This node is activated here, it has no outputs. And also this one, these two ones are deactivated, yes. And randomly we continue doing this, but we in the inference time we use the complete and dense version of this network. It's important. Okay, so it seems some averaging gradients over the reduced neural network during training, and then have the complete network during the inference time. Okay, it's some heuristic. It has some mathematical insights behind it, but the origination doesn't come from mathematics, I suppose. I think the origination and the main insight comes from some sense, it comes from some heuristic. Okay, another important point is that in dropout we train a smaller neural network. When we are dropping some nodes, it means that we make our network somehow smaller. It was the first reason of why orphidic happens. And as I told you, it is random, and because the network is smaller, it's usually do not overfit. Okay, okay, I think it's enough for this one. Okay, as you know, the training is just exactly the same. We compute the forward and backward propagations, and we optimize it exactly like before, and the only change and difference is that some outputs are set to 0, so only the forward propagation change. The back propagation is exactly as before, and yes, and you should know that the probability that we mention is the probability of keeping something, and 1 minus of that probability is the probability of dropout. So if it is 0.9, it means that we keep most of the things and we only drop 10% of the nodes. Okay, so it's dropout code. It's easy, as you can see. It's just a dots entry-wise multiplication, and to remove some of the outputs here in line 4, as you can see here, and in line 3 we have generated, the masks that are randomly generated, and yes, that's it. Okay. Oh, another important note is that we have to scale the weights of each layer with the return probability. You know, uh, you should know that, for example, it's the last iteration of training loop, your t, and we have to multiply it by that probability because it's not as valid as a complete training, because we have deleted something and we have to reduce the importance of this scale weight that we have concluded. Okay, it's somehow an average. We can simply do it by importing torch and torch.nn.dropout, and we usually usually for input layer it is not used, but if you wanted to use dropout for the input layer, you can use the probability 0.8. It means keep most 80% of the nodes and deactivate or remove permanently the temporarily the 20% of the nodes, and for hidden layers it's usually a half. Okay, we can continue with section 3 of chapter 3. Okay, now we want to talk about some data science things. Data preparation that I want to talk about here is very similar to the data preparation parts that we consider in the data science courses. So if you know that, you can skip it. It's something that you may know from data science if you have passed. Okay. Okay. The data preparation is time consuming usually. Don't look at the projects that are on the web and the data set is ready, and the real projects usually start from gathering data, because they, for example, consider a hospital, it should gather information from the patients. Consider a store or a big store, it should collect data from the users, and the users have to agree with the data gathering policy, and it has lots of things. And after gathering the data, you have to process and process the data. I'm going to talk about this stuff. Okay. Okay. We want to talk about how can we as I mentioned to you, preparing data is something related to data science, and yes, but here we are going to talk about it somehow in not very deep, but I think we will get any information that we may need in our projects related to deep learning. Okay, when talking about data preparation, we mean it's a process or procedure of processing data that is completely raw. We recently gathered it, and we want to form something structured and suitable for the model. Okay, there are some things, data augmentation, that we talked before in some, I think 5 minutes before. It means to change data with shift, rotate, transformation, etc. Data cleaning is, for example, we want to remove the unwanted samples, or for example the outliers, the anomalies. Usually the outliers, because anomalies need anomaly detection algorithms. Okay, Another thing is data transformation is different from the data augmentation. Data transformation, we want to make it robust. For example, if the data is not in the range of 0 to 1, maybe we want to escalate or re-escalate. For example, it's somehow adjusting. It's not something very important. It's important in training, but I mean the concept is there. Okay. And another thing that we may want to consider is dimensionality reduction. For example, there are some algorithms that reduce the dimensionalities. For example, we have lots of dimensionalities, and lots of them has very correlation with each other. So we want to reduce the unuseful ones. So we can use the dimensionality reduction algorithms. For example, we can use minimal confusions. Okay. First of all, I'm going to start with augmentation. And as you saw before, one of the causes and reasons of why a model overfits is that the dataset is so small. It was the second reason of overfitting from the three reasons. Okay, we can expand our dataset by the current data. How we can augment it? For example, we have some data and we want to, for example, we do something that, for example, this class would still be this class but with a different data. For example, as you can see here, it has been rotated, it has been shifted in different ways. We can zoom in, zoom out, change intensity, rotate, for example blur. Lots of things can be done here. Okay. Okay, I think that's enough for this part. Okay. We can do lots of data augmentation things. For example, in self-supervised learning, it is not mentioned here, but for example, in self-supervised learning, we don't have any labels, and we want to understand lots of things about the data, and we augment the data, and using contrastive learning, we try to make data and its augmented versions near to each other, and vice versa with the versions and classes that are not in the same class with the data. Okay. For example, we can do geometric transformation like rotating, flipping, cropping, etc. that I talked about before. We can do kernel. We can perform kernel filters to, for example, blur or sharpen or de-sharpen the picture. For example, I'm most here I'm talking with images, but there are some data augmentation techniques for NLP and text too. We can random color, for example, change intensity, exchanging RGB channels. When we exchange the RGB, the overall data remains the same, but the data changes and it becomes more robust. We can remove some pixels and, for example, set values to some reference values. For example, the reference value can be 0 or 256 to 156, 255, and lots of things. And we can mix images. For example, mix two images of cats, and it probably remains cat. And yes. Okay. For example, in audio signal, we can noise inject, we can change sample rate, we can random shift. In text data. We can replace a word with a synonym from the dictionary. We can manipulate the syntax tree and rephrase a sentence. The tree is the same, but it is rephrased. We don't random shuffle it. We can remove and insert some other things. Okay. Okay, and sometimes we have a small data set, but we don't want to manipulate it and change it. For example, as you told you before, we want to generate data. Of course, it's not natural and it is called synthetic. And for example, when we have this formula, an equation of physics, we can generate data by putting some arbitrary v and h inside it and get some d, so this data is generated. Okay. Okay, I think things are simple. We can skip them and another important thing is that you do not to necessarily know the exact function to generate data. Okay, when we want to use some generative models like GANs or diffusion models, and we can generate data from a simple and flat noise, and we'll discuss this later in the final I suppose final slides. Yes, you have seen the data augmentation. I think this part does not have lots of things to talk about, so just some formulations. Okay, and an important thing is data distribution meaning and definition. Is the data distribution means the data that we have generated, and as you know, images have 70,000 images, 60,000 for training and 10,000 for testing. The images are 28 by 28 pixels. Okay, we have something called space of possible data. It is all possible number of data that we can, all possible data, sorry, not the number, it is all possible data that we can generate or can be exist. Okay. Due to the space is easy. Okay, so data distribution is not. I told you before that it is the data points that we have, but is the probability distribution that the data set has been generated from the data space. Okay. We don't have access to data distribution because if we had access, the machine learning approaches were not necessary, and we want to approximate it. Okay. Okay. If the data set represents the data space very good, we can use lots of non-typical data points, or if it doesn't have a good representation, we can transform the data set a better and change the data points, and these are called data cleaning. For example, we can delete the duplicates. It's easy. We can delete the outliers. The outliers can be univariate. For example, if a person's height is 4 meters, it's maybe incorrect, or he may be a special case. Not every people have 4 meters. Or it may be multivariate. It means that, for example, a person can have 2 meters height or 20 kilograms weight, but if he simultaneously has this data, it's not correct, and it's an outlier from the type of multivariate. Okay, we can remove the outliers when we can use loss against these outliers. For example, the loss penalizes itself if it sees outliers. Okay, we are in section 4 of chapter 3. I'm talking about standardization. So we have to normalize and standardize the inputs and features, and that all the variables look the same in all of the directions and dimensions. Okay, we can do input standardization or batch normalization. Okay, for example, if the heights are in centimeters, for example, they are close to each other, but if one of them is the height in centimeters and another is the number of children, they have different ranges. Okay, so as you can see, for example, in example A, the state distributions are the same, but in example B, the empirical risk curvature varies in direction W1, which is x-axis, with W2, which is y-axis. Okay, we can scale them. For example, yes, we can standardize the input. We can reduce the mean of data and divide it by the square root of variance, which is standard deviation. And yes, we don't know the expectation, we can use the mean, and we don't know the variance, we can use the variance some approximation. We can also do a normalization, that we apply normalization like this, as you can see in the picture. Yes, you can see it here. You normalize the data before starting the training, and also in the inference time. Okay, I want to talk about batch normalization. This is very important. It extends the training loop of a mini batch CD, so we can use normalization of hidden layers. We want to approximate the mean and variance using the mini batch, and we want to compute and calculate derivatives by considering the normalization. This is a normal approach without normalization, but we want to have batch normalization. We would conduct these actions, and we scale and shift it, and also yes, and also scale and shift our learnable parameters that are added here. Okay, so the deduction can go something like this, that it is the scale, and it is the it is the scale, and it is the shift parameter, and they're learnable. You can see the batch normalization that has been done here. The standardization has been done, and after that the batch normalization have been done, and you can see the normal backpropagation process that we had before. Yes, this is something normal that you can, I think we can skip them for now. Yes, honestly, it doesn't have lots of things to talk about, and these are direct. Okay, it is the end of chapter 3. We will continue with more interesting things. The next chapter is CNN, convolutional neural networks. It's not as interesting as the next parts after it, but we can tolerate it, and maybe we have a better life after that. Yes, let's see what happens. Thank you for listening and continuing. See you in next chapter. Comment and like for me. If you have any any feedback, please comment me or email me so I can understand. Thank you. Goodbye.